So my co-author is Professor Wei Shi, and he in our team is more of the devices person. So if you have a question in particular about the devices, I'd like to refer you to my co-author. My side of this duo is more on the system side. And so because what you see before you is me, you're going to hear today more about the system side. But our two expertise come together, and I think that by combining the design and the device and the system side, that we're able to come up with better designs and better exploitations of those designs. So I've chosen to talk to you today about two topics. They both involve silicon photonic modulators. In the first case, I'll be talking about Mach-Zehnder traveling wave modulators, and I'm going to discuss how segmentation can be used to achieve several goals. And next, I'll be talking about the smaller, more diminutive microring modulators from silicon photonics, and what are the challenges in working with that device. So let's start with the segmented modulators. So when we come from the devices side, when we look at a specification for a device, we'll learn about the bandwidth and the Vπ. Vπ being the voltage required for a full pi phase swing. Now, as a systems person, I look at that and I say, well, that's really, how do I balance intersymbol interference? Because of, I'm always trying to run my device as fast as I can. I'm always pushing the margin. So how do I balance this with my extinction ratio? And what are the trade-offs that I can make there? Now, when you work in silicon photonics, this is particularly challenging because you often have one parameter you can play with, which is the length of the phase shifter. But playing with that length influences both the bandwidth and the Vπ. And so it's difficult to optimize the two simultaneously. It's challenging. It's not true with the lithium niobate and other platforms, but with silicon, it's the case. It's what's challenging. So suppose I'm on the left and I have a particular length of a phase modulator. I know that that length gives me a certain bandwidth. It gives me a certain Vπ. I know that if I make that length shorter, I will get better bandwidth. But when I change that length, I'm also going to affect Vπ, and I'm not sure I'm going to get the best trade-off. So what can I do? Well, I say I'm going to simplify my life. I'm going to take that length, and what I'm going to do is I'm going to divide it into two portions. So physically divide them into two. But that second one on the right, that segmented one, I'm going to act on it as if it was one phase shifter. So if I want to get zero phase shift, I'm going to apply the same voltage to both of those two segments to pull it down. If I want to pull it up, I'm going to send the same logical signal to both of them at the same time and simultaneously pull them to another phase. What this means is, even though I have split them physically in two, because of my driving strategy, I have effectively not changed the Vπ. So I've kept the Vπ I'm targeting, but now I've divided I've divided it in two, and because of that, I have increased my bandwidth. So I've managed to maintain one and improve on the other. So I showed you two, but of course, I can segment it as many times as I want. But what I'd like to also take the time to show you today is that there's other ways I can use this strategy for different kinds of optimization. I put on the top single segment, that's what an SS means, and multi-segment on the bottom. And I've talked to you already about if I fix the long length and consider just how do I cut it, then I keep the same Vπ, but I get a wider bandwidth. Now on the other side, just looking like the glass half full, half empty, just look at it another way. Suppose I take one of the short lengths and I keep that fixed, and I can either use one of those modulators or I can tile a few of those modulators. So in this case, I'm keeping the same bandwidth because every one of those modulators has the same length, but I'm playing with the Vπ, and I can play with the Vπ to make it larger in this case. So I already talked to you about the case on the left. And just to make sure I'm comparing apples and apples, suppose that I use a drive scheme, whether I'm using the single segment or the multiple segment, so that I'm getting the same signal-to-noise ratio when I get the output. So either device, same signal-to-noise ratio. But when I'm driving the multiple segments, of course, I have to have multiple drive signals. So I did this strategy to have higher bandwidth, which is the title of the talk, so this is going to be the one I'm going to concentrate on. So I get better capacity, greater bandwidth for the same SNR, but of course I'm consuming more power. There's nothing for free. But if I go to the other case, I'm going to compare apples and apples, and I'm going to compare oranges and oranges. Suppose I use the same SNR at the output, or suppose I have the strategy of the same peak-to-peak voltage. If I'm working on a CMOS process and there's a certain peak voltage that I can deal with, maybe that will be the more realistic comparison. Either one will work. Let's start with the same signal-to-noise ratio, like the situation we had in the previous example. So now, basically, I'm going to have the same performance because I have the same signal-to-noise ratio. I have the same bandwidth. I'm going to get the same performance, but I'm going to use less power because to get the same, it's because of the nonlinear power relationship on the three drives and the fact that I can drive the multiple ones lower because I'm targeting the same signal-to-noise ratio. The other way of looking at it is supposing that I'm holding the VPP fixed, so I have the same VPP to all of these modulators, and that will in fact give me better signal-to-noise ratio. So I'm not trying to save power here. I'm trying to increase the quality of my signal. So if I'm limited by SNR, this would be a good compromise to make. So 3 strategies, all using segmentation, but to achieve different system goals. So since the title of my talk is about speed, how to get more capacity, I'm going to give you an example from our experimental work on the first case. So you can see here 3 segments. It's an IQ modulator, so there's actually a mirror of more of these 3 segments on the other side, one for I and one for Q. This is the chip we had fabricated, characterized, and now put them into a systems test. Of course, it's not packaged, so we have to do our own, so the losses are a little high, but still we're able to get our principle out. So as you know, silicon photonic modulators will have different EO responses depending on how we bias them. Another complication using silicon, we ran this at 2 volts bias, which gave us a 63 gigahertz 3 dB bandwidth. This is the systems setup that we had. We did both single polarization, and we used a polarization emulator. We did back-to-back, and we also did some fiber transmission. So this gives you the signal-to-noise ratio versus the bit error rate. You'll see I put 2 FEC thresholds on this plot. I'm showing you the curve here for 16 QAM, which we were able to run at 124 gigabaud. And of course, we were able to stay below both FEC thresholds without challenge. We moved to 32 QAM. We had to make our DSP a little bit more complex. The receiver still getting good performance. And even at 64 QAM at 106 gigabaud, we were able to stay below the 24% FEC threshold. We next moved to exploiting 2 polarizations. And again, 32 QAM was able to get down to the 20% FEC threshold. And in fact, 64 QAM, we just barely made the 24, didn't quite hit it there, maybe the 25% FEC threshold. But in terms of net bit rate, we were getting the best results at the 32 QAM. So in this case, we were able to achieve 1 terabits per second on a single Mach-Zehnder silicon photonics modulator. So having gone through that example, I'd like to switch gears entirely now and talk to you instead about micro-ring modulators. So why do we go to micro-rings instead of Mach-Zehders? Well, because smaller is better. And you say, well, how small? How can I quantify the advantage that I get using a micro-ring modulator? So we use a quantity known as the shoreline bandwidth density metric in gigabits per second per millimeter. And if I were to show you a Mach-Zehnder modulator, we're basically looking at the shoreline. The shoreline here is the distance between the 2 phase shifters. And in a Mach-Zehnder modulator, this is typically about 1.4 millimeters. Now, if I go to a micro-ring modulator, it gets much smaller, like 100 micrometers. And I tried to get this a little bit to scale in the picture, but I don't think it's quite there. Now, there's been much interest in increasing the shoreline density by using micro-ring modulators. And over the years, we have seen this go up from 220 gigabits per second to the previous record, which was 2,000 gigabits per second per millimeter. Now, what I'm careful to do here is to say that these demonstrations were not with IQ MRMs. They were just doing amplitude modulation. So we are going to talk to you today about an IQ modulator. And because we can do advanced modulations format with IQ, that means we can put through more data, which has made us capable of achieving the record for the shoreline density for silicon photonics, where we were able to achieve 5,000 gigabits per second per millimeter. Why is this important? Why is small so important? Well, I'll just give you one extreme example. One way to push the capacity over a single fiber is, of course, to use multiple wavelengths, but also perhaps to use multiple spatial channels. And so there have been some hero demonstrations where we have 750 wavelengths over several bands and 114 spatial channels. So imagine having to have transceivers for each one of those channels. Of course, you need small size, you need small power consumption. And so that is why microring modulators are such intense interest. So over the years, there have been a lot of push to the bandwidth of microring modulators, leading up to 130 gigabaud demonstration of PAM4. Now, if I ask you what has been going on with IQ MRMs, well, you see that's been much more limited, only 25 gigabaud demonstrations. And you can see some of the distortion that might be limiting these demonstrations to QPSK and lower baud rates. So why is there so little work in coherent with microring modulators? Well, there's two reasons. The first challenge is temperature and power-induced instability. Microring modulators are resonant devices. So they sit in, they're easily influenced by changes in temperature and power. The second one is modulation chirp. So I said that there was a distorted QPSK diagram, constellation diagram here. And if you look at the oversampled version, you can see that the distortion introduced by the chirp of these devices. So what I'm going to talk to you about today is how we deal with the first one, which is to demonstrate that we can control and keep this chip stable in order to achieve very high baud rates. And we're also going to look at a new chip design which attacks this modulation chirp very effectively. I'm actually going to talk about the chirp first, and then I'll talk to you about how we implemented the control. So we start with a single microring modulator. You look at the response in power and in phase as you modulate that RF signal, and you can see that the phase is being manipulated at the same time you're trying to manipulate the amplitude. So this is what's giving this sort of curved, chirped trajectory instead of being straight across between the two amplitudes you're trying to achieve. You're actually going through some changes in the phase as well. So, in classic, this is what actually is going to kill you at high speeds and why some of these previous demonstrations were at lower speeds. Now, what we can do classically is we put in a second microring modulator, and we drive that with the negative of the RF in a push-pull configuration. So now this second modulator, you're pulling in the other direction, so the phase shift is going the opposite sense. Because of this, when you look at the net effect, you have these two phase responses sort of canceling each other out, and we get a nice straight trajectory as we published at the conference here. So this design of ours for push-pull is very effective at getting working in a very low chirp regime. So we put these two together in this Mach-Zehnder-assisted microring modulator configuration. Of course, what happens when you get these fluctuations in temperature and in power? Well, when that happens, you're not staying on the resonant frequency the way that you intended to. And so what we do in this case is that we add on-chip photodetectors on the drop ports of these microring modulators, which gives us an observation, an error signal in order to do our stability. Next, we put in heaters so that we can control the drift away from the operating point that we're targeting and bring it back to where we want it. So we use a computer and acquisition card. So we're talking about very, very slow feedback. So although this does add to the complexity of the MRM solution, this is not a super challenging one in terms of the technology required. So I give you all of the components building up to it, and this is a sort of schematic of the full IQ, branch I above, Q below, and each one of the microring modulators in the push-pull configurations, we have 4 rings all together, has its own drop and control signal. So we put this again into a systems test. We run this modulator, had bandwidth greater than 67 gigahertz. It's limited by our test equipment. We can't tell you exactly how wideband it is. This is the stabilization circuit I talked to you about. Now, all the other RF equipment is actually more limited in bandwidth than our microring modulator. So the results I'll present to you today, the bandwidth limitations come from the RF devices rather from the silicon chip. We do one single polarization. We do single polarization as well as double. Let's talk first about the single polarization experiment. In this case, we have a real-time oscilloscope with 2 channels, which is why we were doing the single polarization experiment. We did typical DSP. We used the Nyquist signaling at the transmitter. At the receiver, we did very standard linear processing, no nonlinear processing at the receiver. So again, I'm going to show you, this time I'm going to look at symbol rate, how much I could push the gigabaud and see what the bit error rate is, a couple effect thresholds again on the plot. Started with QPSK, which we could run at 170 gigabaud, got very clean results. We pushed it to 16 QAM and to 32 QAM as well, where we were able to still had to go down a bit on the baud rate to be able to stay beneath the effect threshold. So if I transfer, the symbol rate and what the effect overhead is, I can get the net rate as a function of symbol rate. And we can see that 32 QAM is giving me the best net rate solution for this chip. We next went to a dual polarization experiment. So we put in this polarization emulator. We did some back-to-back, some fiber transmission, and we had to go to a second oscilloscope in order to get 4 channels for our dual polarization. Unfortunately, our second oscilloscope was not as wideband as the first one. So even more constrained in what are the baud rates we could examine with this demonstration. So setup very similar. The only thing that's really changed is which RTO we're using in this experiment. So we couldn't go beyond transmission of 125 gigabaud because of the oscilloscope we were using. But the dual polarization results also showed that we were able to stay under the 20% effect threshold with 32 QAM transmission, which means that our effective symbol rate we could push just to 125, again limited by the RTO. Here's a typical back-to-back constellation diagram, and we also were able to go to 40 kilometers. So if I put these together, 80 kilometers pushed us just above the effect threshold. But if we were targeting 1 terabits per second, we could do that with 32 QAM at 20% effect threshold and a couple different baud rates. We're able to achieve that. So in conclusion, I'd like to say that just silicon photonics can indeed achieve very high data rates. And I propose the systems approach where we can look at both the design and the way we're going to operate these devices. I talked about segmented modulators and how they could be used to increase bandwidth, save on power, or increase signal-to-noise ratio, depending on how you exploit them. I also discussed our chirp-free microring modulator and demonstrated how we were able to achieve record shoreline bandwidth density and 1 terabit per second modulation. And finally, if I could just acknowledge all of the many students, researchers, and funding organizations. Thank you very much for your attention.